Okay, to finish up Unit 9, Chapter 9, we're going to go over permutations and combinations and probability. This is one of my favorite lessons. I enjoy this. I think it's kind of fun to figure these things out. Before you actually watch these notes, it's going to really help you to watch a YouTube video that I posted. It just gives some really good examples of permutations and combinations and the difference. So before you watch this, this is linked in the Unit 1 folder on Blackboard right above, or right below, excuse me, right below these notes. And so if you'll go ahead and pause this and watch this, this lesson will make a lot more sense to you. What it's going to do is it's going to take you to this YouTube video right here. It's 12 minutes. You don't have to watch the entire thing once you kind of feel like you get the gist of it, but it will really show you some visuals that will help you throughout these notes, help it to make a lot more sense. So let's talk about what a permutation is. A permutation is an arrangement of things in a definite order with no repetitions, and order is important. So we haven't really talked about arrangements of things. We've done a lot of probability, we've done some odds. Permutations is we're going to talk about, well, how many ways are there to arrange this? And a permutation is when the order does matter, and a combination is when the order doesn't matter. For example, if I said, hey, I want, on my hamburger, I want pickles, onions, and lettuce. And when I say it in that order, pickles is first, onions, I don't even know what I said. So pickles, onions, and lettuce. So pickles first, onions second, and then lettuce. I want that on my hamburger. Well, what about if I said pickles, lettuce, and onions? In a permutation, the order matters. In a combination, the order does not matter. And so the things that are basically the same but the order is different, we pretty much cancel those out with a combination because the order does not matter. In a permutation, we're looking at things where the order does matter. And so in these formulas that we're going to look at, there's going to be factorials involved. A factorial, if I say n factorial, what that means is you take that number, for example, 5 factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. And we don't want to always write out all of those numbers, and so the factorial means you multiply that number by all of the whole numbers smaller than that. You have the definition there, you have an example there, you have the definition that 0 factorial is 1, and the purpose of what we're doing is to find the number of ways that so many objects can be arranged. So, and the ones that we look at are going to be pretty basic. As you get into more of an upper level class, you would look at these permutations and combinations a bit more complex. There are formulas that I'm going to show you, but on some of these problems that we do, the formulas are not even necessary because we're looking at the basic form of these. And so what I'm going to do is I'm going to go ahead and write the formula for a permutation, although we won't use it much at all because the ones we're looking at are so extremely basic examples. So the notation for a permutation is we're going to have P in here and R here. And if you already watched the YouTube video, you know exactly what this is. The formula for this is n factorial divided by n minus r factorial. And so what we're doing on this is we have n objects and we're looking at r many of them at a time. When we look at these examples, you'll notice that they are pretty basic, which is why we don't necessarily have to write that formula out every time. We end up being able to do the fundamental counting principle. And so the example I give you is how many ways can 7 different types of candy be displayed in a row along the candy aisle. So we have 7 different types of candy, and I want to know how many different ways they can be arranged. And so for this one, what I can do basically is just, okay, when I pick for the first position, how many choices do I have? I have 7. Now one of them's used, so for the second position I have 6. And then for the next position I have 5 to choose from, and then I have 4 to choose from, and then I have 3, and then I have 2, and by the time I get to the 7th position I only have 1 left to choose from, which is basically 7 factorial. And so if I multiply all that out, and some of your calculators will have a factorial in them where you can just hit 7 factorial, but if I multiply all that out, there are 5 6,040 different ways that you can arrange 7 different types of candy. Now, once you put one candy in that first position, obviously it can't be used again, which is why on the next swing you just have 6 choices. And so really, this is known, the note below it, as the fundamental counting principle. If you want to arrange in objects, you can just multiply the number of ways the first category may occur, by the second category, and so forth. And we're going to use the fundamental counting principle on a lot of the problems that we do in this set of notes. So let's go ahead and go down and look at a few more problems. So example 1, we're going to do 3 examples on this first page. It says Sally has 15 shirts, 8 skirts, and 5 pairs of shoes. How many different outfits can be worn? All right, so I'm going to have so many skirts, so many shirts, and so many pairs of shoes, and I want to know how many different outfits. Notice this doesn't say odds or probability. We're just looking at how many different kinds of arrangements. So my first category is shirts. When I go to choose to fill that category, I have 15 options to choose from. My next category is skirts. I have 8 options to choose from. My last category is shoes. I have 5 options to choose from. And so when I multiply all that out, I have 600 different outfits if I have 15 shirts, 5 skirts, and 5 pairs of shoes. The next one's kind of a fun problem. You're definitely going to see it in your My Math Lab homework. License plates in a certain state have 4 letters followed by 2 digits. Part A says, how many different plates are possible if no repetition of letters or numbers are allowed? So in a problem like this, especially if you have it on your test or on your quiz, I'm a very visual learner, and so have to really think about this. I'm going to come up with a license plate. It's going to have 4 letters followed by 2 digits. So I have to do this. I have to say, okay, that's going to be a letter, 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 and then I have a digit here and a digit here. And so I have to think, okay, the first letter, there's no repetitions, which is really big in this problem. So for the first option for my license plate is a letter. I have 26 options. But since there's no repetitions on the next one, I just have 25, and then 24, and then 23. And then when I consider digits, 0 is also digits, so 0 to 9 would be 10 digits because you're including 0. I have 10 digits to choose from here, and then no repetition, so I have 9 to choose from there. And if I use this counting principle and multiply all this out, I have 32,292,000 different license plates that you could come up with if you're doing 4 letters, 2 digits with no repetitions. Now part B changes this slightly because repetitions are allowed. When repetitions are allowed, that would be 26 letters times 26 letters times 26 letters times 26 letters times 10 digits times 10 digits, because you would have all of the options back if you can have repetitions. Obviously this is going to be a bigger number. And so what we have here is we have 45,697,600 different license plates that you could come up with 4 letters, 2 digits when repetitions are allowed. All right, number 3. How many 4-digit numbers can be formed if the first digit must be a 9 and the last digit cannot be a 0? Okay, so again, I'm very visual. I have to think to myself, 1, 2, 3, 4 digits. The first one has to be a 9. The last one can't be a 0. So we know we have 10 digits in our number system. If the first one has to be a 9, I only have one option for that number right there. Only a 9 works. None of the other digits work, so I only have one option there. The second one, this one doesn't say anything about repetition or anything, so I have 10 digits that could work here. 10 digits that can work here, and the last digit I have that it can't be a 0. So if it can't be a 0, there are only 9 digits that would work there. When I multiply all this out, this one's an easy one just to do real quickly in your head. We have 900 different 4-digit numbers that would work, making sure that the first one was a 9 and the last one is not a 0. All right, let's go on to the next page. And, anytime you need more examples, definitely you can go to the PowerPoint or the lecture videos in my math lab or look at the textbook. We're going to do 3 more of these before we really go on, but we're going to kind of start pulling in some probability now. So number 4 says John has 6 DVDs that he randomly places on a shelf. What is the probability that the DVDs will be in alphabetical order? So we have 6 DVDs, and what's the probability that we get them in alphabetical order? Well, first I have to think to myself, out of the, and what I'll get a lot of times on this problem is people will put, well, 1/6, because there's 6 total DVDs. That's not at all what it's asking. If he has 6 DVDs, there's a lot of different ways that those 6 DVDs could be arranged. That would obviously be number of arrangements. It's the fundamental counting principle. For the first one, there's 6 options, and put 1 there, then I have 5 options, then 4, then 3, then 2, then 1, or 6 factorial. So when I multiply that out, there are 720 ways that those 6 DVDs can be arranged on the shelf. Out of that 720 ways, only one of those ways would be in alphabetical order, because there's only one way to do that. There's only one arrangement that would be alphabetical order, but there's 720 different ways that those DVDs can be arranged. So now I'm bringing probability and order together, and what I want now is I want to know the probability that they are in alphabetical order, and that would be one way out of the 720 different arrangements, and that obviously doesn't reduce. Okay, on number 5, we have 2 die that are rolled 4 times, and the sum of the number that comes up is recorded. If you look in your textbook, there's a really good graphic that shows all of the different possibilities of rolling 2 die. And so you can see all those different combinations, like you could roll a 6 and a 3, or you could roll a 2 and a 4, or you could roll, a 6 and a 6. There's all that, but there's a really nice chart that draws all those different combinations out for you if you want to go and take a look at that. What I want to know is what is the probability that we get that the sum is 9? And so I have to think, okay, a dice has 6 sides, numbered, with 1 to 6 dots on it, and I want to know how many of those different ways would add up to 6. And so I come over to the side and I say, well, okay, I could roll a 3 with a 6, or I could roll a 6 with a 3 because, they got the first die and the second die. That's not the same thing. Or I could roll a 4 and a 5 and a 5 and a 4. But when I think about this, these are the only ways that you could roll 2 dice and get that the sum is 9. If you look at that chart and you look at all of the different ways or all of the different possibilities of things that you could get if you roll 2 die, there's 36 different things, 36 possibilities when you roll 2 die. Like I said, you could get the 2 and the 4, you could get a 2 and a 5, you could get a 2 and a 6. And so there's 36 of those. How many of those sum up to 4? So the probability that we have a sum of, I don't know why I said 4, sum of 9, excuse me, that is 4 ways out of the 36 different possibilities there. And then we definitely need to reduce this one to 1/9. Now, if you look at this, here's where you got to take it a step further because we haven't done the last part yet. It says find the probability of getting the sum of 9 on all 4 rolls. So what we did is we found the probability of getting the sum of 9. So I had to think, okay, there's 36 different possibilities. If you look in the book, it's really going to help you understand that. I wrote down all of the ones that add up to 9. And I said, okay, there's 4 of those out of 36 of those different arrangements there. So my probability is 1/9. But that's if we're doing 1 roll. We're doing 4 rolls. So what we have to do now is we're going to have to take that and multiply this 1/9 by itself 4 times because it would be 1/9 for each roll. And so you could say 1/9 times 1/9 times 1/9 times 1/9, or you could do 1/9 4. But we need to say, okay, what's the probability that we get the sum of 9 on all 4 rolls? And that's going to be the 1/9. And I'm running out of space, I apologize. 1/9 to the 4th power. When we multiply that out, that's 1 out of 6,561. And that's a bit more of a challenging problem. You just have to really pay attention to, hey, we're not doing that once, we're doing that 4 times. All right, number 6. In how many ways can the letter in the word teach be arranged? Now, before you go any further, I want you to read number 6, and then down the page, I want you to read number 1. And I want you to notice that they are very similar. Number 6, none of the letters are the same. We have T, E, A, C, H. All the letters are different. When you get down to number 1, the next problem, we're doing the same thing, but with the word Mississippi. The reason we're going to work that differently is because there's repetition of letters. We have more than one I, we have more than one S, we have more than one P. And so when you do your homework, you're going to have some of these problems where all of the letters are different, like number 6. And then you're going to have some of these problems like number 1, right below it, that you work differently because there is repetition in some of the letters, okay? So if I want to know how many different ways we can arrange the letters in the word teach, 5 different letters, it's going to be easy, 5 factorial, 5 times 4 times 3 times 2 times 1. And I'm just going to write it with the factorial notation. So there's 120 different ways to arrange these letters in the word teach, because there would be 5 options for the first letter, then 4 options for the second letter, then 3 options for the third letter, as you go down those categories using the fundamental counting principle. What we're going to look at now, and you can see it here, is we're going to do arrangements, but when we have like objects, when we have repetition, like more than one I or more than one S. And so if we have the repetition, that's where we're going to still do n factorial like we did 5 factorial, but we have to divide out those repetitions to see, because it's really not a different arrangement. When you have, 4 I's to choose from, switching out 2 of the I's is not a different arrangement. And so you have to divide out those repeated objects or letters, whatever you're looking at there. So let's do a couple of those. And if you understand when to use this formula, these really are very, very simple. So on number 1, for these examples, I have the letters in the word Mississippi. When I count the letters in the word Mississippi, there are 11 letters. And so we'll kind of make this easy to understand. So we have n equals 11, because we're going to plug all this up here into this formula. Then I'm going to divide out how many there are of each kind. And basically, I'm only interested in the things that repeat. And so when I look at M, yeah, there's just one M. When I look at I see 1, 2, 3, 4 I's. And so I can call that my R1. My R1, I can say, stands for my I's. And when I consider that, there are 4 of those. And I'm just going to make myself a note that these stand for my 4 I's. The next thing that repeats are the S's. So that's going to be my R2, and there's 4 of those as well. And then my P's, there's more than one of those. That can be my R3, and there are 2 of these. And you might need to go and look at a few more of these in your textbook. You might need a couple more. But really, if you just kind of watch this a couple times, it's really easy. So only use this formula when you're trying to come up with arrangements and there are letters or objects, whatever the problem's talking about, where there's some repetition. So I'm going to do n factorial divided by r1 factorial, r2 factorial, so forth. So that's going to be, there's 11 letters, so that's 11 factorial, and I'm just dividing out the things that repeat. So I'm going to divide it by 4 factorial, and 2 factorial. And then I have to work this out. Your calculator, if you have like a TI 8384, you're going to have that factorial option. Sometimes people can't get these in their calculator real great. So I'm just going to show you what this basically means. This means 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times 4 times 3 times 2 times 1 times 2 times 1, because that gets that 4 factorial, 4 factorial, 2 factorial. The first ones are the i's that are repeating, the s's that are repeating, and the p's that are repeating, because it's not a different arrangement if you're just switching letters that are the same. So you have to divide those out. So when I look at this, I can say, okay, well, this 4, 3, 2, 1 could cancel with this 4, 3, 2, 1. And then I'm basically just doing reducing, and we don't all have to do it the same way. I can say, hey, well, 3 times 2 is 6. I can cancel that with that 6. I can say here, 4 times 2 is 8. I can cancel that with that 8. We don't have to reduce the same way. We should come up with the same answer, though. My denominator is now all ones, so I'm just going to multiply the numbers that are left in the top, and when I do that, I get 34,000. Excuse me, my pen is going crazy. So I have 34,650 ways. All right, 34,650 ways to rearrange the letters in the word Mississippi. All right, let's look at the last one like this, and then we'll go on to the last page. All right, so that's all it's going to go down. All right, in a boat race, there are 4 red boats, 5 blue boats, and 3 green boats. And how many ways can the 12 boats finish if we consider only the colors of the boats? And so when we consider the colors of the boats, well, there's more than one red, there's more than one blue, there's more than one green. So we have like objects, or objects that are the same. Kind of like above, we had like objects because there were 4 S's. So when I think about this, on this one, my N would be 12. And then I have 4 red, 5 blue, 3 green. So I think you'll understand this if I just go ahead and write out how we do this. That's 12 factorial divided by 4 factorial. Sorry, my pen is not collaborated well. So we have 4 factorial, and then we have 5 factorial, and then we have 3 factorial. And so we can write that out. And actually, I'm going to do that on a clean sheet so that you can see it better. So when we do that, that's going to be 12 times 11 times 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. That's the 12 boats. So 12 factorial. It's all the different ways they can come in. But we have to divide out the colors because they're alike. So we had 4 red, so that's dividing out by 4 times 3 times 2 times 1. We had 5 blue, so that's times 5 times 4 times 3 times 2 times 1. And then 3 green, so we have 3 times 2 times 1. And so we're going to say, I always take out the biggest one here, 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. And then we can just start reducing, like here, 3 times 4 is 12, so we can cancel that out there. Here, 3 times 2 is 6. And then I just have a 2 left, so I can say, okay, 2 goes into 8 4 times. And once you've cleared your denominator out to 1, you're just going to multiply your numerator. And that's going to give you 27, good grief, 27,000 and 700, I apologize, 720 ways that these boats can finish if we only consider colors. All right, let's go on to the last page. So combination is an arrangement, but the order makes no difference at all. If you watch the video over the pizza combinations and the restaurant situation there, you're going to completely understand that. If you didn't watch the YouTube video, that's going to be harder for you to understand. And it's very visual, which is why I like for you to watch that YouTube video before we talk about this. So we can use the formula, or we can basically use the fundamental counting principle. I'm going to show you both ways, and then it's completely up to you how you want to do it. So you saw this on the video already. To do a combination, you're going to say, okay, I have n objects, and I'm looking at r objects at a time. The formula is very similar to a permutation, so that's n factorial divided by r factorial times n minus r factorial. And so I'll show you how to use this, but I'm going to also show you what I wrote here in italics. To find the combinations, you can use the fundamental counting principle like we've been doing to get the permutations because they're so basic, the ones that we've done, we don't even really need that formula, and then divide out by the number of ways in which it can be arranged. So I'll show you both. Number one says the Library of Science Book Club offers 5 free books from a list of 50 books. How many possible combinations are there? So there's 50 options, but I'm only getting 5. And I want to know, well, how many different ways or how many different combinations of 5 can I get? So what that's going to be is that's going to be a combination of 50 books doing 5 at a time. This right here is your N, and this right here is your R. So if you do that, that's going to be 50 factorial divided by 5 factorial, and then it's going to be 50 minus 5 factorial. Now, nobody at all wants to write out 50 factorial. So what I want you to understand is right here, this becomes 45 factorial. So up top, 50 factorial is 50 times 49 times 48 times 47 and so forth. The 45 factorial is 45 times 44 times 43. What will happen is 45 down is all going to cancel top and bottom. So when I do that canceling with the 45 down up here, what I have left up top is just 50 times 49 times 48 times 47 times 46 divided by, because the rest canceled with this piece right here, divided by 5 times 4 times 3 times 2 times 1. And this is what I'm saying. If you didn't want to do the formula that way, if you just wanted to do this right here, that's actually this piece right here that I just wrote out. If you wanted to say, okay, I'm going to take the number of permutations and divide it by the number of ways that each can be arranged, when I think here, this top part, when I look at it, is, okay, if I have 50 books, for my first book I have 50 choices. For my second book I have 49 choices. For my third book I have 48 choices. That's the fundamental counting principle. When I divide it by the 5, 4, 3, 2, 1, that's turning it into the combination. And so if you just want to go to this step right here, that's perfectly fine. Either way is good. We've done quite a bit of the reducing, and so what you're going to do is you're going to reduce numbers in the top with the bottom. Like right here, 3 times 2 is 6. That goes into 48 8 times. Here, 5 goes into 50 10 times. 4 now goes into 8 2 times. There's different ways you can do that. But when you multiply all that out, we have 2,118,760 different combinations of 5 books if we have 50 choices. All right, next one. Given a class of 12 girls and 10 boys, how many ways can a committee of 5, we want 2 girls and 3 boys making up this committee of 5, okay? I have 12 girls to choose from, but I'm choosing 2. I have 10 boys to choose from, so I'm choosing 3. So basically, I'm getting a combination of the girls and a combination of the boys, and then I'm going to have to put the 2 together to make the 5. And so for my girls, we'll do that first. That's a combination of 12 girls picking 2 at a time, times for my boys, I have a combination of 10 boys choosing 3 at a time. And so we can use the formula. Actually, on this one, instead of using the formula, let's do the fundamental counting principles. So for the girls, I'm picking 2. For my first girl I choose, I have 12 options, then I have 11 options. So that's just the fundamental counting principle. But I have to divide that by 2 factorial, or 2 times 1. And that's the same exact thing you're going to get if you plug into this formula right here, because you'll see that cancellation that happened with the 50 and the 45, okay? All right, for my boys, I have 10 boys, but I'm choosing 3. So for the first one, I have 10 options, and then the next one I have 9, and then I have 8, but I have to divide it by the 3 factorial, So that's divided by 3 times 2 times 1. And if I multiply all of that out, and I know now that you should be able to do the cross reducing, what we get there is 7,920 ways that we can form a committee from the 10 girls, 12 girls, 10 boys, if I'm choosing 5 people, 2 girls and 3 boys. I do want to go ahead and take a second to show you if you like that formula. I don't want to leave curiosity there at all. I'll just show you this part right here. Here, this is my N and this is my R. So if I'm doing that combination, that's 12 factorial divided by 2 factorial times, oh, this pen is not working well, 12 minus 2 factorial. And you can see here that this turns into 10 factorial. That's going to cancel with the 10 down. So when I cancel this with the 10 down above, that just leaves me on top with 12 times 11 because the 10 down cancels out. So this is 12 times 11. And if you see that, then you can go ahead and just do this piece right here by doing the fundamental counting principle and then dividing it out. All right, number 3, last one. It says, what is the probability of the event that if we have a committee of 5, that it will consist of 2 girls and 3 boys? So this one I think is a bit challenging. I want to explain this as much as I can to you. What we just figured out is if we have 12 girls, 10 boys, we're making a committee of 5. There are 7,920 ways that committee can be made that will have 2 girls and 3 boys, okay? But there's a lot of different committees that we can come up with 5 people. Like, we only looked at doing 2 girls and 3 boys. There could be 1 girl, 4 boys. There could be 4 girls, 1 boy. There's a lot of different other committees that could be created if we consider, hey, we're not specifically choosing 2 girls and 3 boys. And so let me get a clean page here for us to consider that, and then we're actually going to put it into a probability. If I think about, hey, I'm just picking 5 people. They don't even have to be girls and boys. You could have 5 boys, 5 girls, 1 girl, 4 boys, 2 girls, 3 boys, 3 girls, 2 boys. If I'm just picking 5 people at random, what that is that's a combination of, I actually have 22 students in that class, and I'm choosing 5 at a time because I'm not paying attention to boy and girl. So if I consider that, that's going to be 22 factorial over 5 factorial times 22 minus 5 factorial. Or you can look at it like, okay, for the first spot I have 22 choices, then 21 choices, then 20 choices, then 19 choices, then 18 choices. But I have to divide out, because it's a combination and order does not matter, I have to divide it out by, hey, okay, I'm looking at 5 people here. So 5 times 4 times 3 times 2 times 1. And the reason we have to do that is because this is combination. The order does not matter at all. If I worked this out, this would be right here the same thing, because 22 minus 5 is 17. And so the 17 down will cancel, which is how you end up with this right here, however, regardless of how you look at it. Now, if you do all that multiplication, simplify, work it out, what we get there is that's 26,334 different committees of 5 students that we're looking at where we're not paying attention to boys and girls. What I want now, which is the final question, is if I make this committee, what's the probability that I get 2 girls and 3 boys? And so getting 2 girls and 3 boys, remember that was the 7,920 from the last problem, divided by the 26,334 from this problem, and that can be reduced. That's going to reduce to 40 over 133. So that last one's a bit more challenging, but like I said, I like these problems. They're pretty good. Finishing up chapter 9, And if you need any more help, definitely always feel free to email me and take a look at the resources in the My Math Lab multimedia library.